Okay, so let me start today's lecture. Good afternoon. So just again, as usual, we'll start with a little recap. So, so we saw yesterday that, for any rotationally invariant ensemble, you can so which means that the probability distribution of the matrix elements is proportional to exponential minus some constant times trace of some p of h. Okay, so in that case, we could compute the joint distribution of eigenvalues. So this is up to some normalization constant, exponential minus half sum over I equal to 1 to n d lambda I. And then you had this van der Monde factor here, where this index beta was 1, 2, 4 for real symmetric complex Hermitian and complex quaternion unique. We also mentioned that that if you, instead of rotational invariant ensemble, if you take Wigner matrices where with independent entries, you choose the distribution of each entry independently from some distribution. So in that case, in general, it's not easy to compute the joint distribution because you don't have this special symmetry property. However, they are much easier to generate numerically and so on. And so there are, of course, exceptional cases. I mean, there is an ensemble called, I don't have time to discuss that, but it will call the Dumitru-Edelman ensemble. So this is a special type of Wigner matrix for which you can actually calculate the joint distribution. So this is a tridiagonal matrix, but that's almost only exception, basically. Okay, so let me not get into that for the moment. And we also said that there is one special distribution, which is special ensemble, which is the Gaussian ensemble. So that where V lambda, the VH, is just H square. Okay. So that means here you have a lambda I square. So this is the only example which is both rotational invariant as well as it's a Wigner matrix. That means you can choose the entries independently from a Gaussian distribution. Of course, making sure that the variance of the diagonal one are actually twice or half the variance of the off-diagonal ones. Okay? So because the Gaussian ensemble, why Gaussian ensemble is so important to study, precisely because it's both rotationally invariant, which means you can do analytical computation, and it's Wigner, which means you can generate numerically this very easily. So therefore, you can do both numerical and analytical studies for this particular ensemble. And that's why Gaussian ensemble has played a very special role. And from now on in this lecture, I'll just focus only on the Gaussian case, okay? Although, as far as the joint distribution is concerned, you can actually, discuss any arbitrary potential V lambda, but we'll just, focus ourselves mostly on the rotational invariant ensemble, but with V lambda equal to lambda square, okay? Focus on, in general, rotational invariant ensemble. And in particular, Gaussian case. Okay, so in this case, so we know that this is the joint distribution. We'll start from that. So today's lecture is starting from this joint distribution. So once we have this joint distribution explicitly, so let's rewrite this again. You can put a sigma square here, actually, if you like, doesn't matter. But it has to be outside the summation lambda I square. And then you have this lambda I minus lambda j to the power beta, where Zn is the normalization constant, which is as the integral over this, so that the total probability is 1. Now, although for these rotational invariant ensembles, we saw that the values of beta is only 1, 2, 4. It's quantized, this Dyson index. Okay? But there are examples, as I mentioned, for example, this Dimitri-Edelman ensemble, for which you can actually compute the joint distribution, and it turns out that it's exactly of this form, except that this beta can be any arbitrary positive number. Okay? So you can think of now, so I'm going to study this probability distribution, but I'll just assume that beta is any positive continuous variable number. It doesn't have to be quantized to 1, 2, and 4. So we'll think of beta as a continuous parameter. Okay? Continuous parameter. Okay? So what did we do? Just to imagine that we had a full problem of random matrix, and somehow after this change of variable, we got rid of the eigenvector degrees of freedom for this rotational invariant ensemble, and we are focusing on a smaller objects. So this guy had n into n plus 1 over 2 entries, so random variables, but now we are just focusing only on the eigenvalues, which has ensemble of size n. Okay? So once we have that, we can forget about the fact that it came from some underlying random matrix, and we'll just try to analyze this object here. Okay? What can we learn from this joint distribution? So first thing is, this, if I have x to the power beta, I can always write this as a e to the power beta log x, right? So we will use that here to rewrite this as 1 over Zn times exponential minus 1 over 2 sigma square summation lambda I square plus beta log sometimes it's convenient to make I not equal to j and divide by factor 2. Because lambda, if you interchange them, it's the same number. So I can always write it this way. And now, what I'm going to do is to choose the sigma square to be, say, 1 over beta. I can always rescale my lambda I to such that, or you can just choose sigma square to be 1 over beta for convenience, okay? But then you notice that this is just with this rescaling, it just becomes beta over 2, if you like. Okay, let's put it beta. half summation lambda I square I equal to 1 over n plus half I not equal to j log lambda I minus lambda j. So why did you do this? Now this looks familiar to you, right? What does it remind you? Partition function minus beta, very good. So where is the eraser? Yes.
Upper part is nothing but the some sort of action of topological.
No, but let's not get into all these things. Yeah, maybe, but I for the moment I don't want to. Let's just stick to very simple things. Okay, so you have this object here. So I can think of now that I have a gas of particles on a line. Okay, so imagine that this, lambda 1, lambda 2, lambda 3, up to lambda n, or opposite way maybe, I'll do it this way. Actually, let me do it this way, doesn't matter. Okay, so imagine that these are the positions of particles on a line, because these are real numbers. I can think of the position of a particles on a line, and then I have a configuration. So every configuration of such particles is specified by the positions of these particles. And this object which is inside the exponent, so this is like the energy of such a collection of particles of that configuration. Okay? So the energy of such a configuration of lambda is just half there's a minus sign here, sorry. Okay. So what does this energy represent? So there are two terms in this energy function. Okay. So once we have that, okay, so let's just finish this story. So this is exponential minus beta E of lambda I. So this is just the Boltzmann weight of a configuration. So probability of a configuration of lambda i's is exactly given by e to the power minus beta E lambda I by 1 over Zn. So you see that you can interpret this beta as the inverse temperature. One over kBT or whatever. And then Zn is just the partition function. This is a familiar system of equilibrium statistical mechanics, which is just the integral of this exponential minus beta E lambda I d lambda 1 d lambda I. So I can interpret this joint distribution as the Gibbs-Boltzmann weight of a gas of one-dimensional particles. So this is the Gibbs-Boltzmann weight. The joint distribution of eigenvalues, Gibbs-Boltzmann probability. So this is the equilibrium statistical mechanics with a temperature beta, inverse temperature beta. Of a one-dimensional gas of n particles. Okay. So there is some energy. So you give me each configuration of the particles. There is an energy associated with that configuration. And then you just say that the probability of such a configuration is just exponential minus beta E lambda I, right? So what does this energy represent? So there are two terms in this energy. So there is one term which is just lambda I square. So it's like a potential, external harmonic potential. So as if these charged particles, so let me draw it here. So you have these n particles here, okay, these lambda i's, and imagine that there is an external potential which is lambda square. In general, if you have taken other rotational ensemble, you can also think of this as the matrix potential. So this will be exactly the confining potential here. So, but for the Gaussian case, it's just lambda square. So these guys, they are sitting in this external harmonic potential. So this is just the potential energy. Okay? So this is on-site. For each particle feels separately this energy. It's like a magnetic field. Whereas this term is the interaction term. So these particles are not non-interacting, they're interacting. And the interaction term is between every pair of particles. Okay? So you take ith particle and jth particle and look at the difference, position difference. And the sign here tells you that this is a repulsion, right? It's a two-body repulsive interaction between every pair of particles. Why repulsion? Because if lambda I and minus lambda j is very small, log of a very small number is negative, and because of the negative sign, that means it increases the energy. Okay? So this means that these particles repel each other. Every pair of particles, there's a repulsive force between them, and this repulsive force, the functional form of this repulsive force is logarithmic. Okay? So that's why such a gas sometimes is called log gas. Just to analogy of this is, again, if you think of all of you are familiar with Ising model. So Ising model, there, basically you have a lattice, and at each lattice site, you have a spin. Which can be plus minus 1, Ising spin. And so for example, in one dimension, you have a lattice, and let's say you have just, the ith site, you have a spin which is pointing up, and here it's pointing down, pointing down. So the spin configuration is specified by specifying the spins in different sites. So the analog of the spins here are the lambda i's. And then we usually associate energy with an Ising spin, which is usually we take it nearest neighbor, but you don't have to. So Jij, okay, you don't have to take nearest neighbor. In principle, any two spins can interact with each other. So this is the Ising coupling. If J is positive, it's ferromagnetic coupling. If J is negative, it's antiferromagnetic coupling. And then usually we have a magnetic field, for example, H of SI. Okay. So this is a term which doesn't involve couple more than one spin. So this is an on-site term. Okay. Each particle fills the magnetic field, and this is the interaction term which couples any two spins, for example. So if this Jij involve over all pairs, so that's like a mean field Ising model. Okay. All pairs are interacting with each other. But if it is nearest neighbor, then it's the nearest neighbor Ising model. Okay? And then usually you are familiar with in your StatMech basic course that we write the probability of a spin configuration. If the system is in equilibrium at a temperature T, then this is exactly Zn times e to the power minus beta into energy of that configuration. Okay? So this is exactly similar. Here we have a similar sort of systems. I mean, this is the Ising, but you can think of also a gas of particles. In that case, your degrees of freedom will be momentum and positions. You can write the energy, and again, the Gibbs prescription. So in equilibrium stat-mech, it's Mr. Gibbs who told us what the probability distribution at equilibrium should be. Whereas here, we came from a different source. We started with the matrix, and we derived this joint distribution. And we just, the final form is sort of similar to the equilibrium stat-mech problem. Okay? So this is a sort of long-range system, so one-dimensional, long-range because every pair is interacting with every other pair. Okay? So this is a long-range system. Unlike the nearest neighbor Ising model, which is a short-range system. So in that sense, it's more like the mean field Ising model, if you like. But the interaction range is infinite. I mean, everybody is interacting with everybody. All pairs are repelling each other. Okay. So this problem by itself, to analyze just the equilibrium stat-mech of such a long-range system is interesting and it's non-trivial. Okay. It's not as easy as a 1D Ising model. This is already a non-trivial problem, to analyze the properties of this system. So you see there are two levels of complexity in the problem, okay? So this is sort of important to appreciate that. So let me just never mind. So the two levels. So one thing is that you started from the distribution of the matrix entries. And from this, we derived the distribution of the eigenvalues, joint distribution of the eigenvalues. So this step itself is not usually easy, right? We could do it only for rotational invariant ensembles. So that's there's a lot of work people are trying to do, different types of random matrices. You define the joint distribution of the entries, and then you try to compute the distribution of eigenvalues. There's a whole industry, a lot of mathematicians and many other people are working on this, okay? But it's not easy in general. There are few exceptions. Rotational invariant ensemble is one, for which we could actually compute the joint distribution explicitly. So this is if you like, the problem number one, okay? This itself is an industry by itself. But then there's a second step, which is that given this, like we have here, so given this joint distribution, calculate observables. So this is more like equilibrium stat-mech problem. So equilibrium stat-mech problem starts from this basically. We know explicitly the probability of a configuration, which Mr. Gibbs has told us. Okay. And then we try to compute things. For example, the Ising model, you might want to calculate the correlation function. Okay, Cij, maybe connected component. Spin correlation function. This is one observable in Ising model. Then there are many other observables, right? So most of you have studied in your Ising model, stat-mech courses, and we know that this is not always easy. Even though, so here, I mean, our starting point was this. I give you this, Gibbs distribution. I give you the energy function, but starting from that to compute any observable is not always easy. Okay, so we know only exact solutions, only few models, like for example, 1 and 2D Ising model. 3D Ising model is still not known. And okay, there are a few other integrable models for which you can do this computation. So this is not always easy. Okay, so specifying the distribution itself is not easy, first of all, in random matrix theory. But even after knowing the distribution, then it becomes a StatMech problem. And that StatMech problem is not always easy because of this long-range system. Okay? So this is interacting gas or particles. So it's to calculate its observables, it's not always easy. Okay? So this is, but this is the sort of, equilibrium StatMech problem, basically, if you like. Okay? So this is also not always easy. For example, in this problem, it turns out that the beta equal to 2 plays a very special role because you have a lot of structures in the problem which you can exploit for beta equal to 2. But for any other value of beta, it's not always easy to compute, for example, the correlation functions. So let me first define some observables for this Coulomb. So this is sometimes, okay, so before I go on to this is called, I prefer to call it a log gas. Sometimes in the literature you will find that this is called, sometimes also called Coulomb gas, a specific type of Coulomb gas. Now, why is it Coulomb gas? You see, okay, it's not really a Coulomb gas, but just to tell you the difference. So if you have two charged particles, okay, equal, same charge, let's say. So what's the potential? They repel each other, right? Coulomb told us. So what's the potential? Anybody? 1 over r. When you say 1 over r, which dimension are you in? 3 dimension. So so the potential here, okay, between, let's say, 0 and r, goes like 1 over r. R means absolute value of r. And this is the same charge, so it's positive, these things. So this is in d equal to 3. What about d equal to 2? Minus log r. What about d equal to 1? No? Never seen this? It's linear. Okay? And in general, this phi r is actually goes like 1 over r to the power d minus 2 in d dimension. How do you determine this potential? Electrostatics. How do you get 1 over r? Huh? Gauss's law, yeah. Basically, you solve the Laplace's equation, right? Or Poisson equation, if you like. If you take two charges, then it's just a solution of this Green's function, delta function of r. Okay? So if you just take one point charge and you ask how much is the potential generated by this point charge, so I take a charge here and I ask, at a distance r, what's the potential generated here? So that potential satisfies Poisson's equation, right? Charge, I'm assuming charge density is 1, otherwise you'll have minus, okay, whatever, q times delta r. So the solution of this equation gives you the potential, right? And the solution of this equation, okay, this is a exercise. Solution of this equation is precisely this. Phi at a distance r in d dimension goes like 1 over r to the power d minus 2. Okay? So if you take d equal to 1, you get linear. If you take d equal to 3, you get 1 over r. If you take d equal to 2, then you have to be careful because whenever the exponent goes to 0, that means roughly speaking, it becomes a logarithmic interaction, repulsion. Okay? So exercise show this. So, okay, so you see this logarithmic repulsion appears in d equal to 2. Okay? So that means you can interpret this as equally charged particles which are actually living in a two-dimensional plane so that they repel each other by logarithmic interaction, but they are confined on the real line, on one single line. So these guys, imagine that embedding space of 2 dimension. So they're living in these charged particles, living in two-dimensional plane. They repel each other by logarithmic repulsion, but you are constraining in addition to put them on a single line, basically. Okay, so that's why sometimes it's called the Coulomb gas. But you have this extra constraint that they are living on a one-dimensional line, basically. Okay, so that's why I prefer to call it a log gas. Okay, so essentially what we have is an interacting log gas in presence of an external harmonic potential. Okay? And we want to understand the statistical mechanics of this. So for that, we need to define what are the objects we are interested in calculating. Okay? What are the observables? For Ising model, the observables, standard observables are correlation function or magnetization or 1-point function. So magnetization is just a 1-point function. So magnetization for Ising model is just summation SI in presence of a field. So this is like a 1-point function, right? Correlation function, 2-point function. You can define 3-point function, 4-point function. And so these are typically the observables in Ising model, right? So similarly, for this log gas, we have to define what are the objects of interest. You can ask many questions, right? I'm just giving you the weight of a configuration, and you can ask several questions, okay? Several interesting questions. And so let me just list a few of them. To keep this, I can remove this part. So what are the natural observables? Observables means something that you would like to compute or measure, okay? So first thing, okay, just think of the physics. What is this term trying to do? To the origin, very good, okay. The origin is here because that will reduce the energy, right? So what is this term doing? Push them apart, right? So what would they do as a result? They are competing with each other, right? So these two terms compete with each other. So as a result, what would be a typical, if I just close my eyes and pick a configuration, where would they be? They cannot be very far away from very far away from each other. Repulsion is trying to push them apart, right? But of course, if they go very far away, then that will cost energy because of the potential term, right? Because potential term goes like lambda square. So if you go very far away, it will cost a lot of energy. So you can't go very far away. On the other hand, you can't come very close to each other. Can they all come too close to each other? No, because the repulsion is pushing them apart, right? That will also cost energy. Huh?
There is some temperature as well.
Okay, good question. I'll come back to that. No, temperature is not going to play any role here. You will see that. Okay. Because it turns out in this problem, energy is the most important. Entropy is negligible compared to energy in the large N limit. Okay, so the thing is that, okay, so what would they do as a result? So they will actually sit down over a finite region of, they will be separated from each other. but they will settle down in a finite region of space. Okay? That's what will happen. Okay? So to see that, the object that you want to compute, which is the analog of this one-point function, is, so number one, is the density of states, average density, expected. Okay. What do I mean by that? So this is defined by the following quantity. This is exactly what Sanjib was doing in his class. Okay. So what is this object? So this object just counts how many eigenvalues are there between lambda and lambda plus d lambda, right? So I am on my line. I'm asking, okay, I look at a small interval here of width d lambda between lambda and lambda plus d lambda. How many points are there in this small region? Okay, fraction of such points. There are total n points, because if I integrate this object, I've divided by this n such that this is, so what is the integral? Tell me. 1 over n, and delta function, each delta function gives 1. So therefore this is n, so this is 1, right? So this is therefore, you can interpret this as the sort of empirical density, fraction of charges between lambda and lambda plus d lambda, right? What fraction of charges are staying in this interval lambda to d lambda, lambda plus d lambda, okay? So this is called the density of states. And if I now take the average over this, okay, which is the expected value of this, so this angled average here is with respect to the probability measure, which is this guy here, equilibrium measure. Okay? So this means 1 over n joint distribution of eigenvalues, and then you have to integrate over all guys. Okay? But what is this? So this means, so take a particular member of this sum, let's say I equal to 1. So I equal to 1 means that I fix lambda 1 to be at lambda, and I integrate over all the other guys, right? So let's just do it carefully. So this integral, if I do, so this will be p of lambda 1, lambda 2, lambda I minus 1, and then lambda I times lambda I plus 1, lambda n. Right? So I've just integrated over lambda I. So when I integrate over lambda I, so basically in this function you have to replace lambda I by lambda, and then I have n minus 1 integrals, because I've already done the integral over lambda I. So you have just this. Okay? But now you see that as you vary I, this is a totally isotropic distribution, right? Meaning that if I look at my probability distribution here, and if I say that, okay, I fix lambda I to be lambda and integrate over all the other guys, or I do lambda j equal to lambda and integrate over all the other guys, it should give me the same answer, because you can call it, it's a totally permutationally invariant, right? If I exchange any pair of labels, it's exactly the same, it's invariant under that. Okay? So that means this is exactly same for all I, and so the n of them, so it will cancel, and so basically this will be p lambda, lambda 2, lambda 3, lambda n d. So I can as well fix the first guy to be lambda and integrate over all the other guys. Okay. But what is this object here? If you have a joint distribution, when you integrate out some coordinates, what do you get? Marginal, exactly. So this is a one-point marginal distribution, right? Because you are integrating over the n minus 1 coordinates. So what you get is a one-point distribution function, one-point marginal. So this is sometimes not very appreciated, that the average density of states, this is actually true for any isotropic distribution. I didn't use any log gas property anywhere, right? So this is true for any joint distribution, which is invariant under permutation. You can always do this, okay? So this means the average density of states for any permutationally invariant joint distribution is always given by the one-point function, okay? So you see, this is a very natural observable. So we would like to know what is the density of states, how many eigenvalues are there between n and average density of states. So what you would expect, as we are anticipating, that if I plot this guy as a function of lambda, it will be in a confined region, so it will have some shape which we have not computed yet, but you will see that finally it will come into this shape. Okay, we'll try to prove this, and this is the famous Wigner semicircular law. What it says is that the rho n lambda bar in the large n limit goes into a scaling form, which is 1 over square root of n, some function of lambda over square root of n. So there is a typical scale of eigenvalues, which is square root of n, and this function f of z is just 1 over pi square root of 2 minus z square. So what it says is that this rho n lambda is supported only from minus root 2n to plus root 2n, because if lambda, you see the z has so z is between root 2 and minus root 2. So when z is root 2, that means lambda is actually root 2n. So it's supported over a finite interval, minus root 2n to plus root 2n, and it has a higher density near the trap center, and then density goes down on the sides. But we'll prove this. Okay. So anyway, so it already contains a lot of information, which is the one-point function. So then the second natural observer. So this is the analog of, if you like, magnetic field. Okay, in the Ising model. I mean, it's not literally, but this is like a one-point function. Okay. Now, similarly in Ising model, if you have a two-point function, you can define a two-point function here. So how will you define two-point function? Yes? What's the natural question, two-point function? You just fix two guys, right? So in fact, okay, so in general, endpoint correlation function. So it's defined like this. So Rn, n means endpoint. So endpoint means it's a function of n variables, okay? So it's an endpoint marginal, right? Okay, but for some reason we'll clear later, I mean, if I have time, but okay, we put a combinatorial factor outside. This is not very important. And then you just integrate, so you keep the first little n guys fixed at those values, and you integrate over other guys. Okay? So this is just exact generalization of the one-point function. So if you put n equal to 1, so R1 of lambda, n equal to 1, I mean only one argument, so let's call it lambda. So this is just factor n here, because little n equal to 1, and then you have this p of lambda, lambda 2, lambda n, d lambda 2, d lambda n. Okay? And we have just seen that this is just n times rho n lambda bar, right? So you see this factor n here, it just because this was normalized to 1. So n, capital N times this, it means just the average number. So this is just the average number of, not fraction, but average number of eigenvalues in, rho lambda, d lambda basically, okay. Okay. So therefore, this is one-point function. So one-point function is directly related to this density. If I take n equal to 2, so this is a two-point function. So R2, so there will be two arguments. That means, and here I'll get n into n minus 1. I fix the first two guys and I integrate over the rest. You see the meaning of this factor, combinatorial factor n into n minus 1, because it just says that this pair, I could have chosen any n into n minus 1 of them, right? How many I can choose? Different pairs. So that's why they're all exactly same. So that's why you get an overall extra factor, you write it like that, okay? So this is this multi-point correlation function. And these are very important. I mean, in this problem of log gas, they have played a very important role. And what we'll see, I mean, I don't know if we'll see because if I'll have time, but for beta equal to 2, which means the GUE case, Gaussian unitary ensemble, you can compute any endpoint correlation function. As a single determinant, okay? And this happens because of special properties of beta equal to 2, and this is what is called the determinantal point process. So point process means that these points here, you can think of just these points, right? So these points are correlated, as I mentioned, because of this, this factor here, they are repelling each other. So this is exactly in nuclear. Remember my first lecture, I showed you the pictures of this, energy eigenstates of nucleus. In fact, in nuclear physics, it was well known experimentally that the eigenvalues repel each other, okay? And this is exactly what you see here. This is precisely the eigenvalues. This is called the level repulsion in nuclear physics, okay? So this is exactly level repulsion. Effectively, the eigenvalues repel each other, okay? So these points, if there's no correlation, then you just throw these points uniformly, not uniformly, but from independently from Gaussian distribution on a line. That means if you didn't have this interaction term, imagine that you didn't have this interaction term. Then the joint distribution will factorize into individual Gaussians. So that's like saying that, okay, each point I choose from a Gaussian distribution, I throw them on the line. So they are totally independent of each other. So this is like a ideal gas particles, basically, okay? Without the momentum term, it's just energy, ideal gas. But now, because of this level repulsion, so you have this additional logarithmic repulsion between them, which makes the problem much more complicated. And so this process, its process is a misnomer, but this point process, meaning throwing points. So trivial is when there is no correlation between them, but whenever there are correlations between them, such a thing is generally called point process, okay? So points on a line or points on a plane, points in a volume. So this point process, you assign some joint distribution to these points, So such a thing is called point process. Mathematicians like to use this word point process. Now what happens for beta equal to GUE is that all these correlation functions you can actually calculate explicitly, and if I have time I'll show you, and they are called, and you can write them as a determinant, each of them. So any n-point correlation function is an n by n determinant. And that's why there is a name which is called, therefore beta equal to 2 is what is an example of what is called the determinantal point process. Okay, so these are the two observables, 1-point function, which is the average density of states. Then you have generalization of that, which is n-point correlation function. And then even if you don't get to calculate all these things, I don't think we'll have time, but at least you should know what are the interesting observables, okay? So then the next thing that I mentioned again in my beginning lecture, which is the spacing distribution between the eigenvalues. Yeah.
These are not exactly correlation.
Marginal, in random matrix literature, they are called correlation functions. You can call it whatever you like. But even in the Ising model, you can call it a correlation function because what you are is the expected value of under this joint marginal distribution is what we usually call correlation function. But more generally, the marginal distributions are called correlation functions. So spacing distribution, nearest neighbor between neighboring eigenvalues. So that means I look at my gas, I take a configuration, and I compute these distances, okay, between the eigenvalues, nearest neighbor eigenvalues. So this one will be delta 1, this one will be delta 2, etc. And I want to know what is the distribution. So I draw a histogram of these deltas, and I want to know what's this histogram, what's the distribution, right? So I'll define like this: PNS, S being the spacing. Okay, again, or things we'll see in a minute. Let me first write it. Again, this average here is over this probability distribution. So what I'm doing here, what is this thing counting? So this is just the distance between pair of neighboring eigenvalues. So if this is equal to S, you put a delta function, so then that counts those deltas, basically. Okay? So, and then I have to sum over all possible I, because I can take my, this stick here, or I can put a stick there, etc. I just measure, and whenever this stick length hits S, then you have to, and there are n-1 intervals for a given starting point. So therefore, this is the spacing distribution. Okay? This is the object Wigner wanted to first historically calculate, and he just computed it for 2x2 matrix. Okay? So Wigner surmise. Two by two. Wigner said, I couldn't calculate for n by n, it's too hard for me, okay? We just looked at the 2x2 case. So 2x2 case, so let's say beta equal to 2. So what you have is e to the power minus lambda 1 square plus lambda 2 square by 2. And then you have lambda 1 minus lambda 2 square, right? This is the joint distribution, okay, up to some normalization here. So what is the spacing distribution here? You can calculate very easily, right? This object. So P2 of S, n equal to 2. So that means I just have to compute right? That's what this object is. So, since I just have only 2 points, so there's only one interval between them, okay? So this integral immediately, so how will you do that? Again, can somebody tell me? You have a 2-dimensional integral, lambda 1, lambda 2. How will you do? Huh? Yes, change of variable. So define lambda 1 plus lambda 2 as, I don't know, x. And there will be a Jacobian factor which is 2, but that will be absorbed here. So, and this guy you can write in terms of, so lambda 1 is x plus y over 2, lambda 2 is x minus y over 2. So therefore lambda 1 square plus lambda 2 square is 1/4 of 2x square plus 2y square. This is x square plus y square over 2. So therefore, that guy over there would be x square plus y square over 4. This is just a square, some sort of this. Okay, you can write it this way. This will be y square delta of y minus s dx dy. Okay, so then y integral I can trivially do, and x integral will just give me a constant. So basically up to some, okay, it doesn't matter, I mean, because it's the same. So it is y square anyway. So this will be basically s square, okay, up to some normalization constant, calculate this. This will be e to the power minus s square over 4, right? So therefore, it looks like this. So if I plot P2S versus S, the spacing distribution goes like this, and then it falls off as a Gaussian. So here it goes like s square for small s, okay? And this is the level repulsion, right? The probability that s is 0 goes to 0, okay? As s goes to 0, this probability goes to 0, which means there is almost no probability of having the two levels very close to each other, okay? And it decays as a Gaussian for large s. And so this is the picture that we saw in the first lecture with the picture of Wigner. There was a graph there next to it. And so he computed this, and then he gave it to his experimental friends, and they measured with all these nuclear things. And of course, you wouldn't expect, because nuclear physics, this is n by n. N is typically 250 or 238 for uranium. Okay, but nevertheless, it turns out that even for this particular observable, okay, so which means spacing distribution, the n equal to 2 and n equal to 50, once you properly rescale it, it's not that much different. So people know now the exact formula for arbitrary n. Again, you can write as a determinant, more complicated formula. You can compute it exactly. But if you compare with n equal to 2, let's say if you plot p n equal to 100, I mean, you have to rescale things properly. But after rescaling, they differ very, very slightly. Okay, I should draw it the different color maybe. It's hardly, detectable basically. Okay, so which means that n equal to 2 is already a pretty good answer. Okay, of course, I mean it's not exact. I mean you have to, for general n, this is a much more difficult computation, but already n equal to 2 is not so bad. Okay? So this is what is called the Wigner's surmise, because Wigner just surmised that n equal to 2 will be as good as large n, and it turns out to be true, because the large n formula was computed much later, and it was found that when you plot them, you can't really distinguish between them. Okay? So the n dependence is very weak, if you like. Okay, so this is the number 3, it should be. Then what are the other observables? Counting statistics. This is very important. So counting statistics means that you take your gas again. So we have this points. I mean, you can ask for any joint distribution, not just for this log gas, but very generic observables. So I take this gas with its equilibrium weight, and I just look at, let's say, between two, I take an interval, okay? And let me call this interval, I don't know, let's say L1. This location of this point is L1, or I call it AB. Okay? So I look at an interval AB, and I just ask how many points are there in this interval, okay? So let me define this. Number of eigenvalues in AB. Now this is also a random variable because it fluctuates from each configuration to another configuration, and each configuration occurs with this probability. So this object is a random variable. And you can ask, what is this statistics? What is the average value? What is the variance? Or even what is the full distribution? So again, for beta equal to 2, you can compute this full probability distribution, but in general, full probability distribution is hard to do for any other beta. Okay? This object, mean number of particles between A and B, first moment, this is very easy. If you know the average density of states, you can compute this, right? Because what is this? This just counts how many particles are there between A and B, right? So if I know the density of states, so I have to multiply it by n. This is the average density of states. And so this is just the average number of particles between lambda and lambda plus d lambda. So all I have to do is to integrate from A to B. Okay? And if I want to calculate the variance, second moment, let's say n square, then okay, so once again, this is exactly what Joachim was doing and Sanjib was doing today also. You can write this in terms of the indicator function. So for each eigenvalue, I can define, okay, let me write it this way, sigma I. Sigma I is a binary variable. It's 1 or 0. So 1, if the ith eigenvalue lambda I belongs to this interval AB, and 0 otherwise. So then when I take the mean average, so that means mean sigma I. Mean sigma I means it's just this probability that it belongs to this interval AB, which is exactly this 1-point function, right? P of lambda, marginal distribution, and therefore you get back this relation here. If you want to calculate the variance of this in square, so this will involve sigma I, sigma j correlation function because there will be double sum. So sigma I, sigma j is like a 2-point function, right? What's the probability that one eigenvalue is at one eigenvalue, both eigenvalues belong to this interval AB. So then you will have to integrate the 2-point function and so on. So in principle, if you know all this correlation function, you can calculate all the moments of this number of particles in a given interval. But to compute again explicitly is not always easy, except for the case beta equal to 2. But for large n, you can make progress, and that has been sort of made quite a bit. So, but, okay, so 4. And last observable that I want to talk about is, what can I erase? Yeah. So this I had mentioned. This is, there's no analog of this observable usually in Ising model, but here you can ask this question that suppose I look at the lowest eigenvalue or the largest eigenvalue, okay? So lambda max, which is maximum of these eigenvalues. So that means the rightmost particle in your gas of particles. And similarly, you can ask for lambda 1, leftmost particle, which is like the lowest eigenvalue, lambda mean. But for Gaussian ensemble, again, because essentially you have to order these things, but you can show that because of the lambda going to minus lambda invariance, you see this guy has a special invariance, right? If I change lambda to minus lambda, the energy is invariant under that, right? So you have this symmetry, lambda going to minus lambda, which means whatever is the largest eigenvalue and whatever is the the other side. So if you have this average density of states, largest eigenvalue will be typically here, and the lowest eigenvalue will be here, but there is a symmetry lambda going to minus lambda. So the distribution of lambda mean and distribution of lambda max, they will be exactly same, okay? So for Gaussian ensembles, so the P of lambda max and P of is the same probability distribution as P of lambda mean. Okay? And we should remember that our joint distribution was this guy. Okay. Now, why is it interesting to study lambda mean? Some of you asked this question before. So there are many answers to it. So one answer obviously is that, again, if you think of this as random Hamiltonian, then the lowest eigenvalue is the ground state, right? So this is a random disordered system. So the ground state energy will fluctuate from one configuration to another configuration of disorder. And therefore, and it's quite interesting, this is a sort of, if the system is at very low temperature, it's always in the ground state. So, it's important to understand how the ground state fluctuates from sample to sample. So therefore, you are interested in the distribution of lambda mean, which is the lowest, energy of your, because remember this, if you think of H, your random matrix as random Hamiltonian, then these lambdas are just the energy eigenvalues, right? So the lowest energy eigenvalue is just the ground state. So therefore, the distribution of P lambda mean is exactly same as the distribution of the ground state energy. So that's sort of one general motivation. A more sort of more interesting motivation is also, this is one of the simplest cases. Sanjib already mentioned to you, he actually did it in detail, the case of IID random variables, right? So if you did not have this interaction term, imagine that you didn't have the interaction term. So once again, so then it will be, just factorize into different Gaussian distribution. This is like IID Gaussian random variables. So if interaction is not there, and if I'm interested in lambda max of these IID variables, and he already showed you that you have to rescale. So there is AN and BNZ. So you can write down this random variable as AN. So center and rescale it. And then the probability distribution of this rescaled lambda max should converge to the Gumbel probability density for the Gaussian case, right? So if there was no interaction, we would get the Gumbel law, okay? So there's a lot of work these days on the study of extreme value statistics of, in general, correlated random variables. When the variables are independent, IID, you have already heard from Sanjib about these three classical extreme laws, Gumbel, Frechet, and Weibull. So a lot of current research is actually to ask what happens when these are correlated, okay? And this is one of the simplest examples where you see that these guys are very strongly correlated. Everybody is interacting with everybody, right? So this is a, when I in presence of interaction, so this log gas is a system of strongly correlated random variables. And essentially, we know something about strongly correlated random variables, but there are very few systems where you can calculate the distribution of extremes in strongly correlated random variables. So log gas happens to be one of them, very rare, actually. There are other examples. I mean, if you are interested in this, you can look at a review. So this is actually, so I had given a set of lectures on this subject in Florence some time back. And so Arnub Paul was a student here, and then he took some notes, and it's on the archive, okay. 2014. So in these things you will find the other examples of strongly correlated other examples of correlated random variables for which you can actually determine the statistics of extremes. Okay, so this also, I mean, just to connect up with what Joachim was saying today, this will be also the example of, if you don't have interaction, this is exactly the Derrida's random energy model. Okay. Again, in the absence of interaction, so this thing is just Derrida's random energy model. because you just pick each energy independently as a Gaussian random variables. So if you don't have interaction, then this is just exactly the, so this partition function here would be exactly the partition function of random energy model. And random energy model has been studied quite a lot. And so Derrida actually originally computed the distribution of lambda mean for this, but he didn't know at that time the statistics of extremes and things like that, so he did it in a different way, using replicas and so on. But basically when there is no interaction, it's essentially easy problem, okay? The problem comes whenever you have interaction, that means whenever these guys are correlated. So there's a lot of work on this subject, which is currently going on. So it's an interesting subject on its own. So log gas presents one exactly solvable example, okay? So this is exactly solvable for the log gas. So you know exactly the distribution, and this is, okay, I won't have time to talk about this, but I mean, you can look up in the review article that I cited in the website, in the course outline. So this is what is called the Tracy-Widom distribution. And this Tracy-Widom distribution has now appeared in many, many different systems. It has been measured in real experiments, and there's a lot of work on this going on. And but okay, so this is the sort of general motivation that this is an exactly solvable example of a strongly correlated random system. Second motivation I gave you was this, that is a ground state energy of a disordered system in the of a correlated disordered system. But originally, and maybe it's last 10 minutes, I won't have other things to talk. So I'll tell you about this because this I find it very interesting. So again, this will connect up to some extent to what Joachim was doing today. And that is how historically this lambda max actually came about. So this motivation actually goes back to a very beautiful paper by Robert May, who was a biologist, who is a biologist, he's still alive. So this is Nature. So I ask all of you to read this paper because it's really very, very nice and easily readable paper. So this is again sort of to do with the population dynamics, but not in the evolution context, but more behavioral context. So the title of this paper is called "Will a Large Complex System be Stable?" So this is the title of the paper, okay? So what he was interested in the following question. So consider a stable, I'll tell you exactly what it means, non-interacting population of n species with sort of equilibrium population density, if you like, rho I star. So I is going from 1 to n. Okay. So imagine to have a sort of this is, imagine that you have n islands like that, which are totally disconnected from each other. So on each island, you have a species, okay? So here the species number 1 Here is species number 2, species number 3, 4, etc. N. No connection between them, okay? So there is no boat going from one island to another island. They are quite happy. So stable means they are quite happy, which means if you make a small perturbation due to, natural disaster or something, they actually quite stable. That means, if you make a small perturbation, it comes back to its equilibrium density. What this means that if you make, suppose I make some changes due to external perturbation, not due to interaction, and so if the density difference from the equilibrium density, it's a stable, which means what May wrote is just dxi dt, if you like, is deterministic, is just minus xi, let's say. Okay? So that means if you make small perturbation from your equilibrium density, then this xit decays exponentially, the initial value, e to the power minus t, right? So that means you just make a small perturbation to the population density here of species 1. Let's say this is a species of tigers, and maybe this is a species of humans, this is a species of whatever, tortoise and things like that. So they are stable in the sense that if I make small change perturbation, it's not a sort of important perturbation, it is quite robust, it's a stable system. So it comes back with a rate 1 to its initial value. Okay. So it decays in the long time limit to xi goes to 0, that means rho I goes back to its stable value. Okay. So this is the situation when there is no interaction between them. Okay. So now you switch on the interaction. Switch on pairwise interaction. That means imagine that you make links between every pair. Imagine that some ferry or boat service starts going from one island to another island. Okay? So this is, you model it by saying that, so now the question is, once you switched on this interaction, is this system going to be stable? Okay? So this is the question that he was asking. Will a large complex system be stable? Okay? So how does this interaction affect the stability of these systems? Okay? So what you looked at is simply this. So earlier you had this for each I, and now we have an interaction term, which is alpha times some aij, let's call it hij. So this alpha denotes the strength of the interaction, and hij sort of measures the sort of pairwise coupling between the different species. So it's a linear equation, but this hij is a matrix, and he was asking that, okay, what happens if I take this to be a completely random matrix, a real symmetric matrix? I mean, in general, you have no reason to be symmetric, but okay, I mean, he was considered the symmetric case, okay? So real symmetric matrix. And so the question is that, okay, I switched on this alpha. What happens to this population? Is it going to be stable or is it going to be unstable? Okay. So the question is the following. I'll take 5 minutes more, Sanjib, today. Just wanted to finish this. What is the probability that the system remains stable once the interaction is switched on? We know that alpha equal to 0, when there is no interaction, it's stable. Now I switch on this alpha, and for small alpha, you would expect it still to be stable, but as you increase alpha, is it going to be stable or not? So this equation, you can write down as a vector, xi, think of this vector, column vector. right? So this is the H matrix. So alpha H minus this is the identity matrix times X column vector, right? So imagine again that lambda 1, lambda 2, lambda n are the eigenvalues of H. They are real eigenvalues because it's a real symmetric matrix. So what is the criteria for stability? Okay. So stable, so you see, for stability, what you need is that these all the eigenvalues. If I diagonalize this matrix, right? So if I go into the diagonal ensemble, again make a similarity transformation and go to diagonal object. I just make a O transpose O similarity transformation which diagonalizes this matrix. So then you will have this alpha times the diagonal matrix, okay, alpha minus 1. Times whatever. Okay, this I call X prime. Right? I just diagonalize this matrix by going into different bases. Okay? So stability means that all these guys here, all the diagonal elements must be negative, right? Because that means it will always decay to 0. Okay? But if one of them becomes positive, then that means that direction you are going to the perturbation is going to increase. Okay, so it will be stable if alpha lambda I minus 1 is less than 0 for all I. Okay? So this means that all the lambda 1, so lambda 1 is less than 1 over alpha, lambda 2 is less than alpha, 1 over alpha, lambda 3 less than 1 over alpha, and so on, lambda n. Okay? So therefore, probability that the system is stable under interaction is exactly the probability that all these eigenvalues are less than 1 over alpha. But this is, as you have seen, this is just a cumulative distribution of lambda max, right? Because this event means that the largest eigenvalue should be less than 1 over alpha. Okay? So this is just exactly the cumulative distribution of lambda max. So 1 over alpha is just the interaction strength, and you can call it W. And I'll just tell you the results, and maybe we'll discuss later, but I don't know if I'll have time. But what May found is that if you plot this probability, let me call it PWN, or I don't know, yeah, QWN maybe. Sanjib was using the notation Q. So if I plot Q of Wn versus this W, so W, remember, is 1 over the strength of interaction. Okay? So see, if alpha is 0, that means W is infinity. If W is infinity, probability that lambda max is less than infinity, so clearly is 1, right? So here it will be 1. So just plotting 1. If I go W goes to infinity, it goes to 1. Now, if W goes to minus infinity, or actually it cannot be minus infinity because alpha is strength, you can have a negative strength. So W can go to minus infinity. Then the probability that all the eigenvalues will be less than minus infinity should go to 0. So here it must be 0. Okay. And what May speculated, he didn't prove it, but he sort of conjectured that actually there is a transition, phase transition, exactly at a critical value, which is √2. So at W equal to root 2, which means the critical value of alpha C is 1 over square root of 2. So that means, alpha goes to 0 means W is infinity. So the probability that the system is stable is 1. It remains 1, it remains 1. This is in the large n limiter. So it remains stable. So this is again, I'm plotting W equal to 1 over alpha. So as I switched on alpha, so as I'm increasing alpha, that means W is reducing. So as W goes down, it remains stable, up to this critical value root 2. After that, it just becomes unstable. Okay. So when the interaction is strong enough, there's a critical strength of interaction beyond which it suddenly becomes unstable. Okay. And so this root 2 is exactly the root 2 of the Wigner's semicircular law I mentioned. I didn't prove it, of course. And in fact, now what we know is that he didn't, figure out what is the order of the transition. But now we know that this is actually for finite but large n. What happens is that this curve looks like that. And this distribution here, the derivative of that, is precisely the Tracy-Widom distribution. And if you go to the far away, you have large deviation tails, and which I don't have time to talk about. But what I can do is, if you are interested in this subject, you can actually look at this review that I gave in this course outline. So this is myself and Gregory Scher. This is in Journal of Statistical Mechanics, 2014. You can find in the course outline, or you can find it in my homepage also, if you like. Okay? So there's a lot of story going on here. This transition, what we showed is that this is actually third order phase transition. And this third order phase transition has now been found in many, many different systems. But I just wanted to tell you this again. But you see that this is a very natural physical setting or ecological setting in which actually this question of lambda max also appears. Okay? So there's a lot of work going on the largest eigenvalue of a random matrix, both in the physics and maths community. And there are, these are really very interesting and beautiful questions which one would like to study. So what I'll do in the next lecture is that, since I have only one lecture left, I cannot do everything. So I'll just at least, provide you with a derivation of the Wigner's semicircular law. And then if time permits, I want to say a few things about the cold atoms to show you another application of this log gas things. Okay? Thank you.